Hi, uh, welcome to week 5 of the data engineering lectures. I propose I start with a small summary of what we saw last week. So I'm going to share my slides. So we're now in week 5, so that means the second part of our course. So in the first 4 weeks, we saw some fundamentals. So we discussed different data formats, talked about computer architecture, networking, cloud, and last week, data structures and algorithms. So in the next couple of weeks, we have this week and the following 2 weeks on data storage and also on visualization of large amounts of data. And then after that, we'll talk about distributed computing. So remember, in the last 3 weeks, you are going to work on a group project. So there will be no lectures. So last week, we talked about the computational complexity of algorithms, and we introduced two notations, the big O notations and the delta notation for that is used to denote the average time. So both notations are applicable when the size of the input is large. So for small input sizes, the big O notation doesn't help you, but it's used to estimate what will be the execution time given that the size of the input grows. And the same is for the delta notation, where we look at the average time of execution related to the size of the inputs. To give a simple example, if n is 1 million, so that means maybe you have a list of 1 million elements or something like that. We have these 6 complexity classes, either constant time, so ON, which means you're going to do maybe one or a couple of instructions. It can also be logarithmic in n. So here I used logarithmic with 10 as a base. So the log 10 of n of a million is only 6. So if you have an algorithm with a logarithmic worst case complexity, this means you're only going to do a small number of steps. And then the third case was linear. So linear is still fine, given that computers are very fast these days. So with a complexity that's linear, we're going to do about a million compute about a million of instructions. And then we have log linear, and we saw that, for example, for sorting, you can go from quadratic to log linear. So log linear is n times log n. And that means for an input size of 1 million elements, we're going to do about 6 million instructions. So the log 10 of n is 6 times a million is 6 millions. And then the final two complexity classes are slightly harder. So quadratic is still feasible, but it will not be feasible in real time. If you have an algorithm with a quadratic complexity, you can expect that it will take minutes or an hour or something. And with an input size of 1 million elements, yeah, we're going to do 1 billion instructions. And finally, we have exponential problems, and exponential problems are actually not feasible for large values of n. So here's 2 to the power of a million. That's a ridiculous amount of zeros. If you would give that as input in a calculator, it would crash. So clearly exponential problems are not solvable unless n is very small. Then some common algorithms and data structures we saw. So selection sort has a worst case and also average case complexity of n squared. So it's not quite efficient for sorting. And selection sort, you always take the maximum number of a list. You put that at the end of the list, and then you continue with the remaining elements. And you do that iteratively. So you're going to compute n times the max. So that's an n squared complexity. because computing the max takes, the first time you require n steps, the second time you require n-1 step, then n-2 steps, and so on. So it's actually it's n squared divided by 2. But we ignore the constant, so we just say it's an n squared worst case and also average case time complexity. And then we saw quicksort. In the worst case, quicksort can also be n squared, but the average runtime is n log n. So we saw before with if you have a million elements, it will require about 6 million instructions. So quicksort is efficient because it's basically a divide and conquer algorithm where we take the lists, then we partition the list into 2 sublists. The left part is smaller than some number, the right part is larger than some number, and we do that recursively. So then we sort the sublist, and then the sublist, and so on. So given that if you have a good partitioning, if the partition on average divides the lists in 2, then you can expect a runtime that's n log n. Then for data structures, we saw linked list and array list. So array list is used most commonly because of the fast random access. The random access takes only constant time, but you have to be aware when you're going to insert or delete at a random position an element, then you require that all elements after that that index needs to be moved. If you're going to delete, that means you're going to remove the second element. That means the element at the third, fourth, and so on position have to be moved one place to the left. So insert and for delete, it's the same rationale. So insert and delete takes amount of time that's linear in the input. And the linked list has orthogonal properties, I would say. So random access is slow because in a linked list, each cell is linked to the next cell. So if you want to access the 5th element, you have to start at the list, then go to the next cell, next cell, next cell, next cell until you encounter the 5th cell. So random access takes has a worst case that's linear. But if you want to insert and delete elements at a random position, you only have to update the references to the cells. So that takes only constant time. And then we saw 2 more advanced data structures that we will also use today when we talk about relational databases. So a binary tree and a hash table. And in a binary tree, you sort all elements. So it can be numbers, but you can also sort strings or dates. Also, you can have a list of atomic values, but you can also imagine that you have users which have more properties, like the first name, last name, date of birth, and so on, and that you store them in a binary tree, but indexed on their name or something, if you want to quickly search for users on their name. So for a binary tree, insertion, removal, and search take on average log n steps, so that scales quite good with large values of n. Because if you divide your tree, if you divide your numbers recursively in smaller subtrees by having the property that the left subtree always is lower than the element and the right subtree is higher or equal, then you can expect that for a balanced binary tree, the average runtime will be log n. And for a hash table, uses a special trick. So behind the screen, you use an array and then you compute a hash function on a string. And we saw an example of that. And then using that hash function, you can translate any string or number to an index in an array. And then insert, remove, and search take only a constant time on average. So that's a very efficient data structure also. So that was a small recap of last week. So some example exam questions. The first question, if 2 types of algorithms have the same worst best an average complexity, does this mean they take the same amount of time to finish computation? So does anyone want to answer that? Do you know the answer? I'm waiting for somebody to enter something in the chat. No one knows the answer? Okay, there's no feedback in the chat. Well, if they have the, it will be close one, but I think no. Does it take the same amount of time? Yeah, indeed. And so I think the correct, the answer I would expect on this question is that for small inputs, constants are really important. If n is only, if a list has only a size 10, and you have some initialization, or in your loop you're doing a lot of instructions, then the constant factors matter. So even selection sort and quicksort, they have a different complexity, but that doesn't mean that quicksort is faster than selection sort if the input size is really small. So with complexity, time complexity, you're really looking at large numbers of n. And in the limit, if they have the same complexity, that means they take about the same amount of time, but it really depends on the constant factors. So they don't take the same amount of time to finish computation, but they will be in the same order of magnitude. If they're both n squared algorithms, then they will both take about 10 minutes, but maybe one will be 15 minutes because you ignore the constants with complexity. So that's the first question. Yeah. A second question might be provide a pseudocode of selection sort. So that might be a question. So with pseudocode, I mean, you don't have to be exactly correct. I'm not going to grade you on a syntax error or something, but you do have to write a loop and then find the maximum in each loop, and you should be able to provide that pseudocode. And then the third question, assume you want to search for a username in a large list containing about 1 billion of users. Which algorithm would you use and how much time would it take to finish computation? So again, I'm waiting for the chat, if anyone wants to know the answer. What are you going to use? Still waiting. An array list to search. Well, if you use an array list and you want to search in an array, that means you have to go over each user. So you have 1 billion users here, so that's O(n). But indeed, Jordi, a hash table would be the correct answer. So in a hash table, it would only take constant time. So how much time would it take to finish computation? Well, it's a constant time, so it does not depend on the number of users. So maybe it takes a couple of seconds or milliseconds probably, and it's independent whether you have thousands, 1 million, or 1 billion users. So that's indeed the most interesting algorithm. Alternatively, you could say we're going to use a binary tree, and if you take the log 10 of 1 billion, that's only 9. So you can expect that the tree will have a depth of about 9 nodes. So that's also quite efficient. Okay, so this concludes the recap of last week.